Students, all of you, good evening. Welcome to the session. Continuation of circuit theory, that is network theory concepts. I'm discussing chapter 1, that is fundamentals of electrical circuits. With respect to chapter 1, I'm starting lecture 11. In the previous session that I discussed about what is the series connection of resistors, inductors, and capacitors, or the parallel connection of resistors, inductors, and capacitor. How to calculate the equivalent resistances in series connection and parallel connection. How to calculate equivalent inductance and equivalent capacitance in series and parallel connections. How to apply voltage division rule, how to apply current division. Now we have to see the concept of types of sources. What are the different types of sources? The sources are nothing but energy sources. The energy sources are broadly classified into one is direct source, another one is alternating source. These direct sources are again independent voltage and current sources, dependent voltage and current sources. That is independent voltage source, the current source, dependent voltage source and current source. Students, we know that how to represent the direct sources and how to represent the alternating sources. In general, the direct voltage sources are represented like this. You have to see the direct voltage source, direct voltage source representation. A direct voltage source is represented like this. This plus minus V. This one way to represent. And you can also represent like this. This V volts. Or you can also represent like this. This E volts or V volts, that's a battery voltage. This is a representation of direct voltage source. Here, what are the examples of DC voltage? Direct voltage. Here, direct voltage is nothing but a direct source, or direct voltage source is nothing but DC source. The DC sources are cell is the DC source, battery is also DC source, fuel cell also DC source, PV cell also DC source. Cell is one example, battery is also one example, fuel cell also one of the example, PV cell, photovoltaic cell is also one of the example of DC sources. All these are the DC sources, and this is the representation of DC voltage sources. Then how to represent a DC current source? That is direct current source. Direct current source. The direct current source is represented like this. The direct current source is represented. This is the representation of direct current source. Voltage sources and current sources. But we know that practically current sources are not available. In laboratory, we are seeing only voltage sources. But we are not seeing any current sources. But how we can get the current sources? That is practically only voltage sources are available. But how we can get the current sources? Practically, a voltage source in series with large inductor. Yes, voltage source in series with large inductor. It is equivalent to current source. Very important observation. Voltage source in series with large inductor is equivalent to current sources. That is practically only voltage sources are available. But how we can get the current source? Voltage source in series with large inductor is equivalent to current source. These are some examples of voltage sources. Then how to represent the direct voltage source and how to represent the direct current source. How we can get the current source? Voltage source in series with large inductor is equivalent to current source. Students, we know that what are the properties of any DC supply system? A DC supply system is unipolar in voltage, unidirectional in current, no change in phase, and there is no frequency. That is, power frequency is 0, no change in phase also. Here I am giving some properties of DC supply. Just a minute, I am adding the slide. Yes, friends. It's a DC source I'm explaining. That is direct current source. Direct current. DC stands for direct current source. For direct current source that I already given, voltage sources are represented like this. What are the voltage sources? The voltage sources are, that is a cell, battery. Once again, I'm writing here battery, fuel cell, fuel cell. The next one is PV cell. Even you have to take the DC generator, MHD generator. These are the voltage sources. And you know that the representation of voltage sources, DC voltage sources, representation is already given. Clearly, I'm writing here. Representation. This is one way to represent. And we can also use this representation. Or we can also use this representation. This is a direct current sources. Direct current source. The direct current sources representation is like this. The representation. But you know that practically the current sources are not available. A voltage source in series with a large inductor is equivalent to current source. Voltage source in series with large inductor is equivalent to current source. Equivalent. Now here I have to explain what are the properties of DC supply. Properties of DC supply. All of you well known this. There is so many properties of DC supply. Unipolar in voltage and current. Unipolar voltage, only one polar. And unidirectional current. Unidirectional current. Unidirectional current. No change in phase. There is no change in phase. There is no change in phase angle. There is no concept of phase angle. Power frequency equal to 0 Hz. Power frequency 0. I'm talking about properties of DC supply means pure DC. I'm talking about pure DC. For pure DC, form factor equal to 1. Ripple factor is 0. Form factor is 1. Ripple factor is 0. DC supply driven systems are superior with respect to precision, accuracy, portable, compact, easy in control. The ideal DC waveform is like this. Ideal DC waveform. For the representation of ideal DC waveform, it is a represented like this. It is a representation of ideal DC waveform. And this is voltage. This is T in seconds. Then where we can use this DC supply? You have to see the applications of DC supply. Applications. There is so many applications of DC supply. You know that for charging of the cell phones, we have to use the DC only. Cell phones. For cell phones, battery charging. Even some toys also have to use the DC source. Machine tools also we have to use the DC supply. Machine tools. You can also use in automobiles. That is in automobiles. Machine tools, automobiles. You can also use in electronic board apparatus. Electronic board apparatus. Medical instrumentation. In medical instrumentation also we are using batteries. All these are the DC. Medical instrumentation. You can also use in wireless technology. Wireless technology. Wireless technology. So these are the applications of DC supply or DC source. Then what the AC supply? AC supply system. That is alternating current supply. AC stands for alternating current. Alternating current supply. AC supply is alternating current supply. What are the properties of alternating current supply? What are the properties? If you have to see the properties, it is a bipolar voltage, positives off cycle, negative off cycle, bipolar voltage, bidirectional current, bidirectional current, so bidirectional current, definite change in phase, definite change in phase, change in phase. Power frequency exists, power frequency is exist. There is existence of power frequency. Ideal AC waveform is sinusoid. You know this ideal AC waveform. Which is the ideal AC waveform? That is a sinusoid. This is our ideal AC waveform. The sinusoidal is the ideal AC waveform. In detail about this waveform, we'll see in the AC analysis. But this ideal AC waveform. Very popular. What are the applications of AC? Generation, transmission, distribution, utilization, power level. We have to make the transmission, distribution in single phase and three phase also. Mainly distribution is single phase, transmission is three phase. In some cases, distribution also three phase is also there. But utilization, both single phase and three phase is there. If you have to see the applications, so that is a generation, transmission, distribution, utilization. The form of AC, utilization at power level, at power, at power. But if how to represent this voltage source and current sources in AC supply? In AC supply, voltage source is represented like this. It's a representation of voltage source in AC supply. Here this is voltage source representation, plus minus this is voltage source. Then how to represent the current source? The current source is represented like this. This is the current source representation. This AC current source is represented like this. This AC current source representation. To follow this representation. This AC voltage source and AC current source. But point to remember, instantaneous values are represented with small letters. Instantaneous values are represented with lowercase letters. Average and RMS values are uppercase letters. That is, we have to use small letters. This uppercase, that is, we have to use the capital letters. Average and RMS values are represented with uppercase. That is, we have to use the capital letters. Our instantaneous values are represented with small letters. That notation you have to follow. This supports some introduction with respect to AC supply and DC supply. Here I given direct source and alternating source. This is DC supply. Alternating source is AC supply. Now we'll see in detail about first we have to see direct sources. The direct sources are independent and dependent. In independent, there is independent voltage source is there, current source is also there. Independent voltage sources are there, current sources also there. First we have to see independent sources. I am discussing the DC sources. About the AC, we'll see in the second chapter. Okay, first we have to concentrate DC sources. The DC sources are independent sources. Independent sources are those which do not depend on any electrical parameter but may depend on time. That is, based on the time only, the source, how much voltage is supplying, how much current is delivering will change, but it is independent of the on any electrical parameter. That is called independent sources. These are again voltage sources and current sources. The voltage sources are ideal voltage source, practical voltage source. Current sources are ideal current source, practical current source. Here I am discussing the DC sources first. In DC sources, independent sources, dependent sources. First I am starting independent sources. Why the name is given as independent sources? Which do not depends on any electrical parameter, but may depends on the time. That's why name is given as an independent sources. It depends only on the time. It is independent of the electrical parameter. Now I have to see independent voltage sources. The voltage source which can deliver constant voltage, to the circuit as independent of the current flowing through the source. Whatever may the current in the circuit, it delivers the constant voltage. Then it is nothing but an independent voltage source. See, for example, this is the independent voltage source of 10 volts. This 10 volts. Whatever may be the current, this voltage remains constant. How much voltage it delivering? 10 volts it is delivering. It's supplying how much? 10 volts it is supplying. Whatever may be the current. That is, the voltage is independent of current in the circuit. That is equal to 10 volts. See, for example, this supplying the plus minus 2 into e power minus 15. This supplying the V voltage. Whatever may be the current, this is the voltage. This is the independent voltage sources, that is independent of the current flowing through the source. Next, you have to see in independent voltage sources, again there is a two types of voltage sources: ideal voltage source and ideal current source. Ideal voltage source. Independent voltage source with zero internal resistance is called ideal voltage source. Independent voltage source with zero internal resistance. Therefore, for ideal voltage source, very important. For ideal voltage source, internal resistance or input resistance. For the internal resistance or input resistance equal to 0. Input resistance equal to 0 for ideal voltage source. Whatever may be the current in the circuit, that this is Vs. Ideally, it supplies the constant voltage. This is I. Whatever may be the current, whatever may be the current, always this V equal to Vs. That is called ideal voltage source. That is with respect to time. At any time, this source supplies the voltage of Vs. This source supplies the voltage of Vs. That is called ideal voltage source. Whatever may be the current, the voltage remains constant. If you draw the characteristics for ideal voltage source, you have to draw the characteristics for ideal voltage source. This is I, and this is minus I, this is V, and this is minus V. Whatever may be the current, it may be positive current or negative current, whatever may be the current, the voltage remains constant, that V equal to Vs. V equal to Vs. These are the current. This voltage, whatever may be the current, current in the circuit, current V equal to Vs. This is called ideal voltage source. That is, there is no any drop. The internal resistance equal to 0. Then what is the practical voltage source? A practical voltage source having some amount of internal series resistance are known as practical independent voltage source. That is, the internal resistance equal to or input resistance for practical voltage source. For practical voltage source, internal resistance or input resistance. For the internal resistance or input resistance. Internal resistance or input resistance equal to small input, very less input resistance, very less, or small input resistance, or very small. Ideally, 0 means practically very small. For ideal voltage source, 0 input resistance. For practical voltage source, very small input resistance. That is, once it is having small input resistance, then practically the voltage source is represented like this, plus minus Vs. That the internal resistance or source resistance is Rs. That this current is I. So this is the V voltage. This is the V voltage. Like plus minus. This is the plus minus. And apply KVL in these loops, friends. Have to apply KVL in this. If you apply KVL, positive to negative, negative, minus I into Rs, minus V, plus Vs equal to 0. From this, what is V equal to? Vs minus I into Rs. I into Rs. Shall I write like this? You have to write from this I formula, I into Rs equal to Vs minus V, Vs minus V. From this, what is I equal to, friends? I equal to Vs by Rs minus V by Rs. Minus V by Rs. That is, if you draw the characteristics, I and Vs, I and V, this is I, this is minus I, this is V, and this is minus. Slightly it is reducing. Just like y equal to mx plus c, y equal to mx plus c, minus V by Rs plus Vs by Rs. What the slope? It's just like mx plus c. The slope equal to minus 1 by Rs. Minus 1 by Rs. Then actually the characteristics are slight line. The voltage remains constant. But here we are getting the characteristics like this. These are the practical characteristics. Practically, IV characteristics are like this. This is the slope of reduction. At what slope it is reduced? Minus 1 by Rs. It is reduced by slope of minus 1 by Rs. Clear. If you draw the characteristics with respect to time, here I draw the characteristics with respect to voltage is constant. That is ideal case. But practically, slightly reduction. This is V. Practically, it is not Vs. Ideally, the voltage remains constant at whatever may be the time. With respect to time, slightly it is reducing because of this resistance drop. These characteristics are with respect to time. These characteristics are IV characteristics. That you have to consider. Yeah, this practical voltage source and practical. Here, practical voltage source and ideal voltage source. Next, independent current source. The current source which can deliver constant current to the circuit as it is independent of the load. Independent voltage sources, it delivers the constant voltage. Independent current sources, it delivers the constant current. It delivers the constant current. Yeah, that is nothing but a independent current source. Say for example, this is the one current source, friends. This is 10 amp. It delivers the constant current. Whatever may be the voltage, it delivers the constant current. It is also current source. This 10 into e power minus 5t. It delivers the constant current. This also current source. But this is the AC current source. It is the AC current source. It's 50 sin omega t. 50 sin omega. Then it delivers the constant current. As independent of the load voltage. Whatever may be the load voltage, this current remains. But it depends on the time. It depends on the time. Now you have to see ideal current source, ideal practical current source. Independent current source with zero internal resistance is called ideal current source. Independent current source with zero internal series resistance. Internal series resistance. Internal series resistance is called ideal current source. But parallel input resistance or internal resistance equal to infinity. This is very important observation here. How to see? This is the current source representation. This is the current source representation. Yeah, this is I. Let this is Is. Whatever may be the voltage, let this is the V. The voltage source is V source. Then here I equal to Is. With zero internal, you have to take instead of internal series resistance. With zero internal leakage current. The zero internal leakage current is called ideal current source. Means here there is no any leakage current means then what is the resistance offered in this path? This is the infinite. Parallel resistance is infinite. That is parallel input resistance or internal resistance. Parallel input resistance or internal resistance. Internal resistance. Internal resistance equal to infinity. That is parallel input resistance or internal resistance equal to infinity. Then I equal to Is. If you draw the IV characteristics for this case, if you have to draw the IV characteristics for this case, this is I minus I V. Whatever may be the voltage, load voltage, it supplies the constant current. This I equal to Is. Whatever may be the current, whatever may be the voltage, supplies the constant. This I equal to Is. The current remains constant. If you draw with respect to time, if you draw the characteristics with respect to time, whatever may be the time, that I remains constant. I equal to Is. This is ideal current source. A parallel input resistance or internal resistance equal to independent current source with zero internal leakage current or parallel input resistance is infinity, then it is treated as an ideal current source. But what are practical current sources? Sources having some amount of internal parallel resistance are known as practical independent current source. See this one. But practical input resistance is infinity. But this ideal input resistance is infinity. But practically, it is having small parallel resistance. That is, there is some leakage current. Like this is the current source. This is the current source. And parallelly, it is having some resistance, internal resistance. This is Rs. Some amount. It's not a small resistance. Practically, it's a high resistance. Ideally, infinity means practically high, sir. That point of view. That is having a high value of parallel resistance. Practically, input resistance or internal resistance. Input resistance or internal resistance. Internal resistance is high value. Practically, infinity means, ideally infinity means practically it is a high value. Now, the source applying Is current. This Is current. Let whatever may be the voltage V, let this supply voltage is V. Sorry, not supply voltage, load voltage is V. If it is V means here also it is V. And there is some current like this and remaining current I is flowing. Now apply nodal analysis here. Later on I will explain. You take the KCL here or nodal analysis. Entering current is minus Is. This leaving current is V by Rs. This also leaving current is plus I equal to 0. Entering current is minus Is. This is V by Rs. This is I. From this, what is I equals to? Is minus V by Rs. Is minus V by Rs. This high value of parallel resistance. High value of parallel resistance. Very small leakage current. Parallel resistance. Then I equal to Is minus V by Rs. V by Rs. That is Is minus, it's just like Y equal to Mx plus C. To write like this. Minus V by Rs plus Is. This Y equal to Mx plus C. The slope of reduction is minus 1 by Rs. If you draw the characteristics for practical current source, this is I minus I, V minus V. This is exactly straight line. But there is a slight reduction in the current. Then you can get the characteristics like this. The slope of reduction is, what is the slope of this? Minus 1 by Rs. It is reduced with a slope of reduction of minus 1 by Rs. Here this, how to see ideal current source, practical current source. Ideal voltage source is characteristics. Practical voltage source. Practical with respect to time also you have to draw. To draw the characteristics with respect to time also. This is I equal to Is. Ideally, practically slight reduction in the current because of having some parallel resistance. This is about the concepts you have to remember with respect to independent voltage source, current source, ideal voltage source, practical voltage source, ideal current source, practical current source. These are the independent sources. Next, you have to see dependent sources. A dependent source is a voltage source or a current source whose value depends on voltage or current elsewhere in the network. See the definitions. A dependent source is a voltage source or it's a current source. There is a dependent voltage sources are available, dependent current sources also available, whose value depends on the voltage or current elsewhere in the network. Elsewhere in the network. That is nothing but a dependent sources. The dependent sources are so many types of dependent sources are available. So many types of dependent sources. That is the dependent sources are dependent voltage source and dependent current source. How to see the dependent sources are that is voltage sources and dependent current sources. Dependent current sources. In dependent voltage sources, there is a voltage controlled, current controlled voltage sources. Voltage controlled voltage sources, current controlled voltage sources. Current controlled voltage sources. That is voltage controlled voltage sources, voltage controlled voltage sources, current controlled voltage sources. Current controlled voltage sources. Current sources also again voltage controlled current sources, voltage controlled, and there is a current controlled current sources also. Current controlled. That is voltage controlled current sources, current controlled current sources, voltage controlled current sources, current controlled current sources. It's a representation of current controlled current sources, current controlled voltage sources, voltage controlled voltage sources, voltage controlled current sources, voltage controlled current sources. Clear? I have to see how we can represent voltage controlled voltage sources or voltage dependent voltage sources. Correct. Next, voltage controlled current sources are voltage dependent current sources. First, I'm writing, but these are represented with a symbol of this is a diamond symbol. We are using them. How these dependent sources are represented? We are representing with a diamond symbol. But represent like this is a representation. First, I'm writing this one. VCVS, VCVS, or it is also called VDVS. What is VCVS stands for? Voltage controlled voltage source. Voltage controlled voltage source, or it is also called voltage dependent voltage source. The another name is voltage dependent voltage source. Voltage dependent voltage source. And this is the example for voltage dependent voltage source or voltage controlled voltage source. Represent like this. Is plus minus K1 into Vx. K1 into Vx. Where Vx is the some voltage in a network. Where Vx equal to some voltage in a network. At any branch. Some voltage in a network at any branch. Then this voltage controlled voltage sources. This is voltage controlled voltage source. And this is the linear. Voltage controlled voltage source is it's a linear voltage controlled voltage source. Linear voltage controlled voltage source. See, one more is I'm writing. To write voltage controlled current source, VCCS or VDCS. VDCS. Voltage controlled current source. Voltage controlled current source. Or it is also called voltage dependent current source. Voltage dependent current source. Then what is the representation? This voltage controlled current source. The voltage controlled current source is represented like this. This is how to use, not circle, how to use the, for independent sources we are using the circle representation. For dependent sources we are using the diamond symbol. Is a current source, but it's a voltage controlled current source. Let some K2 into VA, where VA is the some voltage in network. Some voltage in network. Then this also linear. This is a linear voltage controlled current source or voltage dependent current source. One more example and one more source I am writing. Current controlled current source, CCCS, or it is also called CDCS. That is current controlled current source. Current controlled current source. Or it is also called current dependent current source. Current dependent current source. Current dependent current source. Then how we can represent this one? Current controlled current source. Current controlled current source. How to use the diamond symbol? Like this. Some K3 into Ix. Where Ix is some current in a network, in any branch. Some current in a network. Current in a network at any branch. It is also linear. Okay, this current controlled current source. Voltage controlled voltage source. Voltage controlled current source. Yes, the fourth one is current controlled current source or current dependent current source. Now, last one is current controlled voltage source, CCVS, or current dependent voltage source. Current controlled current source. Sorry, current controlled voltage source. Current controlled students voltage source. Or it is also called current dependent voltage source. Current dependent voltage source. Current dependent source. Then how it is represented? It is a current controlled voltage source. It is a voltage source. Voltage source means plus minus. Some constant K4 into current controlled. Current controlled means you have to take IY. Where IY is some current in the network at any branch. Some current in network at any branch. At any branch. Clear? Next. This is current controlled voltage. Current controlled voltage source. Voltage source means plus minus. Easy to current control or current dependent. It is also linear. There is a linear dependent sources are available. Non-linear dependent sources also. I am writing one of the example for non-linear source also. Current controlled voltage source. Current controlled voltage source. Current controlled voltage source. For example, if the current controlled voltage source is given like this, it is a voltage source now plus minus. It is a current controlled some constant K into later it is given K5 into I1 square it is given. K5 is the constant K5 into I1 square it is. Same current controlled voltage source already given. This is current controlled voltage source. Current to controlled voltage source. Now which one, friends? This is current to controlled voltage source. Current to controlled voltage source. But what is the difference here? It's a parameter is IY only, but square parameter I1 square. That's why it is a where which it's a non-linear. This source is a non-linear. That means in dependent sources there is a linear is available, non-linear is also available. It is a non-linear control. Current controlled voltage source is a non, but it is a linear control. Yes, this mainly how to consider. These are the different types of dependent sources. These are the different types of dependent sources that you have to concentrate. Next. Here I given some important statements with respect to dependent sources that you have to concentrate. Dependent sources are useful to represent an equivalent electrical models for many electronic devices such as transistors, operational amplifiers, and integrated circuits. We can use this. I think you know in H parameter representation, Y parameter representation, Z parameter representation, we are using the dependent sources. That is, we can use in representation of many electronic devices, such as transistors, operation. We can use the integrated circuit representation. We can use dependent sources. That is one point we have to remember. With respect to controlled variable only, the dependent sources are said to be linear, active, and bilateral. The presence of these elements makes the network linear and active and bilateral. The presence of these elements make the network is a linear, active, and bilateral also. But based on the control parameter only, how to tell that it is a linear or non-linear? It is a non-linear, but it is a linear based on the control parameters. Control sources are said to be sources, that is, active elements in the presence of at least one independent source. Then only control variables are non-zero and hence their magnitudes are not. Very important. Control sources are said to be sources, that is, active elements. When the control sources are said to be active elements, in the presence of at least one independent source in the circuit or network, if one independent sources is present, at least one independent, then only it is treated as active element. Then only control variables are non-zero and hence their magnitudes also non-zero. Very important. The controlled, that is, dependent sources are active. The circuit must be consist of minimum one dependent sources. Sorry, one independent sources. Dependent sources are active. There is a minimum one independent source. All are dependent sources. That circuit is totally passive, not active. If all are dependent sources, that circuit is totally passive. There is no any active. If there is no any independent source. If there is an independent source, then only the dependent sources are the active elements. Then only the dependent sources are the active elements. This statement is very important. Please remember this 5-star statement. These three are very important statements. With this knowledge, before starting the source transformation, I have to explain what the equivalent circuits with respect to sources. How to write equivalent circuits. Very important observation. Equivalent circuits with respect to sources. With respect to sources. What are the equivalent circuits with respect to sources? See, for example, two voltage sources is plus minus V1, plus minus V2 connected in series. Then what is the resultant you have to write? The resultant equal to V1 plus V2. You have to replace as a single source with V equal to V1 plus V2. Directly you can add and replace with a single source. Very important observation during solving of the problems. Next. For example, if it is given like this is plus minus V1 and this is minus plus V2. Then let's assume that V1 greater than V2. V1 greater than V2. Then how you can replace this? The voltage which is high value, you have to take that polarity one. This is plus minus. Then resultant V equal to V1 minus V2. The voltage which is high value, that polarity only have to take V1 minus V2. This is equal to. Same, one more I am giving here. Two sources, plus minus V1. This is minus plus V2, where V2 greater than V1. Then what is the resultant you have to replace? Which is greater? V2 is greater. Then you take V2 polarity. Minus plus V equal to V2 minus V1. V2 minus. Next. Fourth one. During solving of the problems, all these observations are important. For example, if two voltage sources, this is plus minus V1 plus minus V1 and this also plus minus V2. These are equal to plus minus V1 equal to V2 equal to V. Then only you have to connect in parallel. This is equivalent to V1 equal to V2 equal to V. Then only this combination is exist. Otherwise, the combination is not exist. See, for example, this is plus minus 10 volts. This also plus minus 10 volts. Then what the resultant V equal to? Plus minus plus minus. Equal voltages are parallel. Then V equal to 10 volts. That is the answer. V equal to 10 volts. See, I am giving one more example. If it is given like this, This is plus minus 10 volts, 10 volts, and this is plus minus 5 volts. Then what the resultant V? Can anybody? Plus minus 10 volts, plus minus 5 volts. Anybody? If you apply KVL in this loop, if you apply KVL students, if you apply KVL, what you can get? Positive to negative, minus 5, negative to positive, plus 10, equal to 0. 10 equal to, is it 10 equal to 5? No. Is it 10 equal to 5? No. That's why KVL is not valid. KVL is not valid. That's why the sum is not equal to 0. KVL is not valid. Hence, physical connection is not possible. This type of connection is not possible. Physically, this connection is not exist. That is the answer. Physically, why KVL is not valid? Physically, this connection is not valid. Clear, friends? This connection is not valid. Physically, this connection is not. You have to connect the two voltages are in parallel. These two must be equal. If two voltages are equal, then only parallel is exist. Two voltages are equal and same polarity, plus minus, then only parallel connection is existing. See, for example, if it is given like this is plus minus 10 volts. One more source it is given, minus plus 10 volts. Then what is the V? Can anybody? What is the V? Can you apply KVL in this loop? If you apply KVL, negative to positive, plus 10, negative to positive, plus 10, equal to 0. 10 plus 10 is equal to 0? No. That's why KVL not valid. 10 plus 10 equal to 20, but the sum is not becomes to 0. That's why KVL not valid. Therefore, physically this connection is not exist. Even the voltages are equal, but polarity is different now. This is plus 10 volts, this is minus 10 volts. Or if it is a plus, it is a minus. Two different voltages never be connected in parallel. Always equal voltages are connected in parallel. That's why physically this connection is not valid. Because KVL is not applied, not valid. This connection is not exist. This connection is not exist. Here also you have to write physically this connection is not exist. Not exist. Physically this connection is not. Physically this connection is not exist. Yes, friends. When it is exist, voltages are must be equal, polarity is also equal. Then only the connection is exist. Then only the connection is exist. For example, two sources are connected in series. One more example. This is 10 volts. This is plus minus 20 volts. Both are same polarity. What the resultant equal to? That is plus minus, same polarity, that is 30 volts. That is the answer. Plus minus 30 volts. Two different voltages you connect in series. For example, if they given like this, plus minus 20 volts, minus plus 40 volts. Then what the resultant? Which is greater? Minus plus is greater. You have to take that polarity one. Minus plus. That is 40 minus 20. High minus low. 40 minus 20. That is 20 volts. 20 volts, but polarity is minus plus, not plus minus. Because which is high voltage polarity only you have to take. That is the 20 volts. Like that you have to answer. Clear? All these are with respect to sources. I'm telling that with respect to sources. That is voltage sources. So for example, if current sources are given, one more note I am giving. That this is I1. How to take this I1 and this is I2. Two different current sources connected in parallel. Then what the resultant I1 plus I2. Different current sources you have to connect in parallel. I1 plus I2. Now replace with I equal to I1 plus. For example, this is 1. This is I. This also I. But the resultant that this is you have to take some current. This is I1. This is also I. Then what the resultant I? Resultant I is not 2I1. Resultant I is I1 only. Because in series connection, current remains constant. Don't add the current. In series connection, you have to add the voltages based on the polarity. Polarity is different, you have to subtract. Current remains constant. For example, if they given two different current sources, Let this is I1, this is I2. What is I? Where I1 not equal to I2. If I1 is not equal to I2, then two different current sources are connected in series now. This connection is not exist. Physically, like this. Physically, this connection is not exist. Don't connect two different sources, two different current sources in series. This connection not exist because KCL is not valid. This connection is not exist. See, for example, if it is given like this is 10 ampere. This also 10 ampere. Can anybody tell what is I? Then I equal to 10 ampere. That it's not 20 ampere, it's 10 ampere. I equal to 10. One more example. That this is 10 ampere. This is 20 amperes. Can anybody tell what is I? What is I equal? Not exist. Physically not exist. Physically, this connection not exist. Why? Two different currents. This connection not exist. Not exist. Physically, this connection is not exist. Two different voltages never connected in parallel. Two different current sources never connected in series. That's simple. But two different voltages connect in series. Two different current sources connect in parallel. No problem. See, for example, friends, this is 10 amperes. This is 10 amperes. And this is 20 amperes. This is parallel connection to different current sources. Then what the resultant I? Take the always high current direction, just like high voltage direction, high current direction. This is the I1 current and this is I2 current. I2 greater than I1. I2 greater than I1 means then I2 minus I1. That is 20 minus 10. This is equal to 10 ampere. 10 ampere this direction. This is the resultant current direction. The current which is high value, that direction only you take. Clear, sir? That direction only how to. 20 minus 10, that equal to 10 ampere. Clear? Two different current sources, series not valid. Same current sources are valid. Two different current sources in parallel is valid. Same currents are valid. Two different current sources in series is not valid. Clear, students? Like that you have to. See, for example, I'm asking one question. Can you try this? I'm expecting answer from you. This is plus minus 10 volts. Plus minus 10 volts. And this is 5 ohms. Plus minus 5 ohms. 5 ohms. The current through 5 ohm resistor is dash. Current through 5 ohm resistor is dash. 5 ohm resistor is dash. Current through 5 ohm resistor is dash. Yes, please. Option A, 1 ampere. Option B, 0.5 amperes. Option C, 2 amperes. Option D, this connection is not exist. This connection is not exist. Can anybody? I'm expecting answer from you. Plus minus 10 volts, plus minus 5 volts. What is the current through 5 ohm resistor? Very good. Option D is the correct. This connection is not exist. Why? Two different voltage sources never connect in parallel. Two different voltage sources never connect in parallel. That's why this connection is not exist. One more model I'm writing here. Can you try this? This is plus minus 10 volts. This is 5 ohms. Plus minus 10 volts. Plus minus 10 volts. This is I. Current through 5 ohm resistor is dash. Current through 5 ohm resistor is dash. Option A, 2 amperes. Option B, 4 amperes. Option C, 1 ampere. Option D, this connection not exist. This connection not exist. Can anybody? What are the answers? Come on, do it. 10 volts in parallel. Two different, it's not two different sources, na? Same sources. Even polarity also same. Then if two equal voltages are in parallel, resultant is 10 volts only. This is equivalent to like this. This is 5 ohms. Then you find the current. 10 volts parallel is equivalent to 10 volts ohm. Then what the current through 5 ohm resistor? 10 by 5. How much? 2 amperes. Option A is correct. Told now. V1 equal to V2. Two voltages are equal. Then V1 equal V2 equal this equal to V. You replace with a single voltage. You replace with a single voltage source. If V1 equal to V2, then you have to replace with a single voltage source. Then current through 5 ohm resistor equal to next. One more example I am framing here. For example, this is 2 amperes. This is 2 amperes. And this is 3 amperes. 3 amperes. And this is the resistance. And this is 5 ohms. Plus minus V. This V not equal to dash. Option A, 25 volts. Option B, so this 5 volts. Option C, 15 volts. Not exist. That is, this connection is not exist. What are the answers, friends? Come on. Fraction of minute you have to answer. Again, no need to check the KVL, all this. Two different current sources never connect in series. Two different current sources never connect in series. Two different current sources never connect in series. That's why, what is the answer? Not exist. This is not exist. For example, one more I am giving. This is 3 amperes. This also 3 amperes. This resistance is connected here. Plus minus V0. But V0 equal. Option A. This is 5 ohm resistance. This is a 5. 15 volts. Minus 15 volts. 30 volts. Not exist. Can anybody? I'm expecting answer from you. I'm expecting answer from you. Option B. Very good. It's a minus 15 volts. That is correct. 3 amperes, 3 ampere in series. Resultant is 3 amperes only. It's not a 6 amperes. The current direction is given like this. According to current direction, this is plus, this is minus. Then, according to current direction, this V0 equal to, this is plus, this is minus. That is 3 into 5. But this polarity and this polarity is opposite now. According to current direction, this is plus, this is, but given polarity is plus minus, opposite. That's why you have to take minus. This is minus 15 volts. Clear, friends? 3 resultant is 3 only, not 6. In series connection, current remains constant. This is 3. 3 into 5, 15. But according to current direction, this is wherever the current is entering, this is plus, this is minus. But this is plus minus. Opposite now. That's why minus 15 volts. Say minus 15 volts. Any doubt? Clear? Like this you have to consider. These are the observations with respect to voltage sources. Here I am giving 2 more points. First one. For example, a current source in series with resistance. Like this is the R1 resistance. This is the load. If the current source is I, the current through R1 is also I. After R1 is also I. There is no drop in the current. Current remains same. That is, a resistance in series with the current source is, a resistance in series with the ideal current source is neglected. But this R1 is considered only in power calculation. A resistance in series with ideal current source. Ideal current source is neglected. But in series the ideal current source is neglected. The second point is this R1 is considered only in power calculation. This R1 is considered, but R1 is considered in power calculations. In current, no need to consider that. One more observation. If there is any voltage source, plus minus V, across this any resistance, parallel resistance is present. then also voltage is V. You no need to consider drop across R1. This is V means across the R1 is also V in parallel connection. This V naught equal to V only. That's why a resistance in parallel with ideal voltage source is neglected. A resistance, yes, a resistance in parallel with ideal voltage source, ideal voltage source is neglected. So it's neglected. But it is considered, but R1 is considered, in power calculations. Power calculations. The R1 is considered in power calculations. Third. Say for example, this is a current source. This is 10 ampere. If there is a resistance of 5 ohms, that this is what the current flowing through 2 ohm resistance. Current flowing through 2 ohm resistance, 5 ohm resistance. 5 ohm. What the current flowing through 5 ohm resistance? Flowing through 5 ohm resistance. Option A, less than 10 amperes, greater than 10 amperes, equal to 10 amperes, not exist. What is the answer? The current source supplying the current of 10 amperes. What is the current through 5 ohm resistance? Can anybody? What is the current through 5 ohm resistance? A current source, it's ideal current source. Independent of load voltage or load, it supplies the constant current of 10 amperes only. It's not less than 10 amperes, it's not greater than 10 amperes. It supplies the constant current of 10 amperes only. Clear, students? Supply the constant current of 10 amperes only. Like that we have. Clear? See, for example, simple question I am framing here. This is 10 amperes and this is 20 amperes. 20 amperes. This 5 ohm resistor. This 20 ohm resistor. Can anybody calculate what the V now? Come on, do it. 10 ampere, 20 amperes. Then what is the V naught? Constants. The solution for this is 10 ampere, 20 ampere, parallel, opposite. Always the direction is higher current direction only. This is the direction. 20 minus 10, 10 ampere. This is a 10 ampere. There is a 20 minus 10, that is a 10 amperes. Now, what is this resistance? 5 ohms and 20 ohms is parallel. 5 into 20 by 5 plus 20. What are the R equivalent, students? 5 into 20 by 5 plus 20. What is the R equivalent? 4 ohms. Okay, this is the 4 ohms. Now you tell me what is V naught? What is the V naught? This is 10 amperes. The current here also 10 ampere. Plus minus. That is V naught equal to 10 into 4. But this polarity and this polarity is opposite, minus. This is equal to minus 40 ohms. Minus 40 ohms. Clear? Any doubt? Or otherwise, this current is 10 ampere. This current is 10 ampere. If you want, another method also you have to solve. This one method. This is method 1. Here I am giving method 2. Any method you have to follow. This 10, 20 opposite, this is 10 ampere. Always the current is high current direction. This is 10 ampere. This is 5 ohms. This is 20 ohms. How to find this V? that this current is 10 ampere. This is I1. This is I2. Can you find what is I1? Current division rule. 10 into opposite resistance by total resistance. How much? 200 by 25, 8. This is 8 amperes. Can you find what is I2? 10 into opposite resistance by total resistance. Total resistance. 50 by 2. This is 50 by 25, 2 amperes. This is 2 amperes. The current is 8 amperes. Plus minus. Plus minus. Current is 2 amperes. 2 into 20, 40. 8 into 5, 40. Voltages are equal. Parallel connection voltages are always equal. Like that only current is divided. Clear, friends? Finally, you can get 41. This is plus minus. V naught. You calculate this voltage or this voltage. Voltages are in parallel connection is equal. Is equal to minus 40 volts. Like this also you can do. Apply the current divider rule. Or you have to find what is the parallel of these two, and you find this. Yeah, this is the information about the sources. Now, with this knowledge, we go for the source transformation technique. That is one concept. And one more concept is star to delta, delta to star conversion. That is one concept. After that, we go for the different models of questions before starting model analysis and mesh analysis. Yeah, this is about the today's session. Any doubt? Tomorrow I'll continue with source transformation. Friends, any doubt? Okay, if you don't find it out, I'm ending the session. Tomorrow we'll continue. Thank you.